Dear friends, students and learners, I am Shashank from the School of Engineering Technology in the Gandhi National Open University. So in the previous session, we have taken up the unit of ceramics, refractory and abrasive materials, and in that we discussed the starting part, which comprised of certain thermal properties, and also discussed about insulators and certain refractory materials. Now we will take up a very important refractory material that is known as the ceramics in this session. So we are discussing about ceramics, and ceramics are basically inorganic crystalline materials which are characterized by certain properties like low ductility and high melting point. So these ceramics have low ductility, high melting point, they are brittle, and these materials are processed by methods other than melting. They are not prepared by melting process. These ceramics consist of metallic as well as non-metallic elements, and these types of elements are bonded together by either ionic or covalent bonds. So these things you must have read in your 12th class chemistry or before that, this ionic and covalent bond. So these ceramics are generally produced by powder compacting. This is the production process of ceramic, and sintering. Sintering means coalescing them at a certain temperature, meaning bringing them together, like you prepare your floor in the house, in the kitchen, similar to that. And in general, ceramic materials are hard and brittle. Like we said earlier that low ductility is there. So low ductility means it is brittle and it is hard also, and toughness is low and ductility is low. And they have got an inability, that is to deform plastically. Obviously when they are not ductile, so they will not be plastic as well. And it happens, what happens in the inner structure actually, due to the directional ionic and covalent bonds, they leave no free electrons. So due to the lack of the free electrons, they are not plastic. Due to the insufficient number of electrons, again the same thing we are discussing, insufficient number of electrons, another thing comes in, that is they become bad conductors of heat and electricity. This is quite obvious, because our electricity conduction is based on the movement of electrons only, and their engineering application makes use of electrical and thermal insulating properties. So since they are not good conductors of heat and electricity, they can be used as insulators. The inherent chemical stability and strong bonding make ceramic quite capable of surviving in hostile environment. So actually in the molecular structure they have a very good chemical stability and a strong bonding is there. So they can be used in hostile environment or high temperature applications. Now we should get to know about the ceramic constituents. What are the constituents for making ceramic? So basically there are three things, that is clay, silica, flint and feldspar. So these are the basic ingredients of traditional ceramics. So we discussed the first one now, the clay. So main constituents of clay are the hydrated aluminium silicate, meaning the silica form of aluminium, that is aluminium silicate, they are both combined, and it has water also, certain water also, and it is given here is a combination of Al2O3, SiO2, H2O. The small amounts of other oxides like those of titanium, iron, magnesium, calcium and potassium are also present. So this is the clay. All these things make the clay. Then silica. So silica, what it is? It is basically SiO2, that is silicon dioxide, and it provides stability against high temperature. So that's how ceramic becomes good at high temperature. Third one is the feldspar, which is a combination of potassium oxide, aluminum oxide and silicon dioxide. Like in clay the potassium oxide was not there, but in feldspar potassium oxide is there, and this produces glass bond between the refractory components. Traditional ceramics applications, actually in case of ceramics we can say like traditional ceramics are normally used in form of tiles and bricks for construction or as electrical porcelain for electrical insulators. So you may have seen all these things in your practical lives. So in bricks and like in furnaces, and also these type of refractory materials are there. Then you may have seen in your houses also these electrical insulators, like in fuses. The fuse is there in the house, so it is generally made of ceramic. So as a electrical insulator, this material is very highly standardized for this industry, electrical industry, and large variations are also available. So it is a very good application of this ceramic material. Another class identified as engineering ceramics typically are made up of pure compounds like aluminium oxide Al2O3, silicon carbide SiC, and silicon nitride, that is Si3N4, the chemical formulas. So these engineering ceramics are used for high temperature applications. So the engineering ceramics are used for the high temperature applications. So now we come to the point of refractoriness. We have been using this term refractory for so many times. So what it is actually? Ability of a material to withstand the action of heat without appreciable deformation or softening is referred to as refractoriness. So any material, if heated and it doesn't undergo large deformation or appreciable deformation, or no softening within the material takes place, then we can use it as a refractory material. This property is measured as temperature at which the refractory material softens or fuses under some load. So as soon as we reach a temperature where this material is softened or fused, and then we can know the capacity of that refractory material. The refractories are those materials which can withstand the action of hot environment, whether it be liquid or gaseous, both type of things it can withstand. So there are industries which are engaged in manufacturing of metals, like we discussed earlier, the steel and all, iron, ceramics, glass and chemicals. So these depend heavily upon using these refractory materials, because we need either prevention of heat leakage, or we need to transmit it at a higher rate. So heat is a very important thing. So whenever we want a certain kind of insulation, then refractory materials can come into picture. So what is the composition of the refractory materials? Most refractory materials actually are ceramics, like we have discussed ceramics and their subdivision also. So refractory materials are ceramics, and this constitute of high melting oxides of what? Silicon, aluminium, magnesium, calcium and zirconium. So I have told these things earlier to you also, to you. There may be other elements also which may present as impurities. For high temperature applications, crystalline oxides, carbides, borides and sulfides are employed. Such materials are sometimes combined with metals to produce a substance known as cermets, which have better shock resistance than pure oxide or carbide refractories. So a combination of these may be better than the pure oxide as well, in case of shock resistance especially. So these cermets are used in gas turbines, because there also we get shock. Suppose there is sudden cooling and all those things. So in gas turbines it can be there, in steam turbines also, ramjet engines, missiles or nuclear reactors. So wherever there is a possibility of shock, we can use this cermet. Further, we are discussing certain refractory materials. These are made up of engineering ceramics, as we have discussed earlier, but they are very expensive also in pure forms. So these materials are also difficult to form. Forming cannot be done for these materials. Most industrial refractory materials are made of mixture of ceramic compounds, and these compounds, as we have discussed earlier, these are heat resistant because of their high melting point. The compounds that are most widely used in industrial refractory materials are alumina, Al2O3, and silicon nitride, silicon carbide and zirconium oxide. And other refractory oxides are also there, which are mixed with these compounds. And these refractory materials, how they are identified? They are more identified by their compressive strength and flexure strength. So their tensile strength and ductility is not that good. They are brittle, but they have very good compressive strength and bending strength also, meaning their failure in bending is not happening every now and then. But we should keep in our mind that these are brittle, like I have told you just now. These are brittle materials and they cannot yield consistent values of strength, particularly tensile strength. Tensile strength is not good, and they don't give a fixed value or exact value of tensile strength. Why? Because of the presence of several defects, micro defects are there. Thus we have to adopt a statistical approach if we want to know the tensile strength or the load which this member can carry. At the same time, it can also be understood that larger components with larger surface area will have higher probability of carrying crack-like defects, and hence large sizes must be avoided. So whenever we are using certain refractory material, we should see that too large size should not be used, because the tendency or the probability would be more of having a crack in it. So there are experimental methods for tensile strength determination in case of ceramics, but they do not prove efficient, and for this reason what happens, we use 3-point bend test, which are better strength indicator, because they are giving us the flexural strength, which is very important in case of ceramics. The modulus of elasticity of these materials is quite high, often as high as 1000 to 2000 times the tensile strength. So elasticity is still high. The tensile strength may be not high, but elasticity is still very good. The modulus of elasticity is largely dependent upon the level of porosity and proportion of impurities. So it will depend, modulus of elasticity will depend on, one thing is porosity and the other one is the proportion of the impurities. So what is the kind of behavior, what is the typical behavior of these ceramics at high temperature? So ceramics may not sustain certain load at low temperatures, but the same load may be sustained beyond certain high temperature. So it's quite a unique thing that at low temperature they may not be good, but at high temperature they are good. Why? The reason for that is that this phenomena occurs because of the tip rounding of crack-like flaw at high temperature. So if you take a specimen, there may be a small crack, and it may be expanding at high temperature. So what will happen, that this rounding of this flaw happens. Suppose it is a very sharp section, so it will turn into circular or round form, and thus what will happen, the stress concentration factor will come to a finite value from infinity, because in case of very sharp section, stress concentration factor is very high up to the level of infinity. But as soon as we give a curve, or like you must have read somewhere else in your engineering drawing or anywhere else, that if we give a fillet, then this stress concentration decreases. So similar thing is here also, rounding effect will decrease the stress concentration. For alumina, this temperature at which ceramics become very good is 1400 degrees centigrade, while for silicon nitride it is 1600 degrees centigrade. So this was the reason, and this is a very unique property of ceramic, they are very good at high temperature. So this refractory metals oxides now we will discuss. There are certain oxides, and these include the alumina, the aluminium based one, magnesia, there is magnesium based one, zirconia, beryllia and thoria. Other oxides are also there, but they are very sparingly used because of high cost, and these are like yttria, ceria and hafnia. Variety of shapes in oxide refractories can be obtained by the process of slip casting. So slip casting process is applied to get different shapes oxide materials which are used for refractories. So what is the production process for these refractory oxides? There is a process in which fine particles of oxides are mixed in temporary organic binders. And what are these temporary organic binders? Like the starch, latex, wax or polyvinyl alcohol. Then this mixture of the two is molded into desired shape, created in plaster of Paris mold. So there is a plaster of Paris mold, and in that this mixture is poured. And further we wait for drying. After the mold has dried sufficiently, it can be handled, and it is fired at a temperature of about 1800 degrees centigrade. Why we are using this high temperature? Because they are better at this high temperature. Ceramics are better formed. At this temperature, the fine particles sinter rapidly, meaning they come together, coalesce together very rapidly. facilitating the solid surface reaction between fine particles. The resulting material is self-bonded refractory of coherent structure. They are very tightly bonded now and they are self-bonded by their properties only. This bonding is achieved. And the self-bonded refractory of coherent structure is formed whose refractoriness approaches that of the material itself. So even after sintering and coalescing, the refractoriness can be as good as the original material itself. This mixture refractoriness is as good as the original material. So there are other methods of production also. So some of these are listed here. The first one is pressing, then isostatic pressing, and then the final one is the hot pressing. So the simple pressing, what happens here? The raw particulates are pressed dry or wet into a die of desired shape. This is the process applied. When we have isostatic pressing, here particulate material is pressed in all directions by hydraulic pressure against flexible walls of shaped container. So we take a container, a shaped container, and we are applying pressure from all directions equally. And this part obtained is fired to achieve the desired strength. And the final method is the hot pressing. In hot pressing, the compacting and sintering occurs simultaneously. The force may be applied axially or it may be isostatic. So now we discuss about certain metal oxides, different kinds of them. The first one is alumina. Alumina is the hardest type of oxide, Al2O3, and because of its hardness, where can we use it? We can use it for resistance against wear. And at high temperature, wear phenomena is very common. So this alumina is very good at this temperature because it is helps us in wear resistance. It is also markedly low porosity and very high strength. So as soon as it has low porosity, so the microstructure will be free of pores and it will thus lead to higher strength. Its application, actually it is used in pyrometer tubes and spark plug insulation and crucible for melting metals and glasses. For those of you who may not be knowing what is a spark plug actually, so spark plug is used in IC engines. So those related with mechanical engineering can know that. And IC engines are internal combustion engines, the petrol engines you can say, and it is known as the spark ignition engine also. So there we use a spark plug for giving ignition. So there are very high temperatures and this alumina is used there. Alumina is also used for high quality electrical applications. Why? Because it has low dielectric loss and high resistivity also. Further moving on, we shall now discuss about beryllia. It is beryllium based. It has also got very high melting point and it is high resistance to thermal shock and is inert to carbon and carbon monoxide. So this property of high resistance to thermal shock and its inertness to carbon and carbon monoxide is very useful, especially up to 2000 degrees centigrade, because then there will be no reactions. And further we discuss the magnesia, which is magnesium based oxide, and it is characterized also by very high melting point of around 28 degrees centigrade, but it has high vapor pressure, so its use is restricted to around 2200 degrees centigrade in oxidizing atmosphere and to 1700 degrees centigrade in reducing atmosphere. But it has higher thermal conductivity, greater refractiveness, and is also better resistance to basic slag. So slag formation is lesser when magnesia is used, and it is very good against corrosion at high temperature and is also used for electrical purposes because it can be used as an insulator. Then the next oxide is the zirconia oxide. This one also has a very high melting point of 2700 degrees centigrade. So you can see all kinds of oxides which are used for refractory purposes have very high melting points because otherwise they cannot be used. But this one, zirconia, this cannot be used in very high temperature. Why? Because it loses its resistance to thermal shock at a temperature of about 1100 degree to 1300 degrees centigrade. So the thermal shock phenomena occurs at a lower temperature in case of zirconia. And why it happens? Because Due to polymorphic transformation, monoclinic crystals of zirconia are formed from denser tetragonal form. Thus, they result into volume expansion and tendency to crack. So, cracks can occur. But one positive thing is there, that the structure of zirconia can be stabilized into cubic form. When it goes from tetragonal to monoclinic, then it's dangerous. But when it goes into cubic form, then it can be stabilized. Zirconia can be stabilized. And how it is done? By addition of foreign elements like calcium oxide and magnesium oxide. Also, by adding 9% of magnesium oxide with a special heat treatment, a partially stabilized zirconia can be obtained. And this partially stabilized one actually improves the fracture toughness. So this is very good actually. Zirconia products are used for oxygen probes. These are some applications in small crucibles and in dishes, and for heating elements in air at high temperatures. Further on, there is one more thing, that is thoria, which is thorium based. This one also has very high melting point, and its application is in the melting of platinum. It is used for that purpose. But the drawback is like that it is limited to small sizes because of high cost, and also because of the difficulty of shaping. So shaping thoria is difficult. So after discussing the various kinds of oxides which are used as refractory materials, we can now come to the carbides. So what are the important refractory carbides? These are like silicon, boron, zirconium and titanium. So we have the zirconium oxides, similarly we have zirconium carbide also, and both can be used as refractory materials. Although the carbides have very high melting points, they lack oxidation resistance. But this is a drawback of carbide, that they are not oxidation resistant. So what can happen? Corrosion and rusting type of thing can happen. So the very first carbide we can discuss here, that is silicon carbide. It is very famous also, and also known as carborundum, and is used for various purposes. Its properties as such are like very high hardness, very high refractiveness, high thermal conductivity and semiconducting nature also. So silicon we know is used as semiconductors also. Electrical conductivity for this is low at low temperature, but increases by order of magnitude at high temperatures. So quite a similar behavior like we have done earlier. Thermal conductivity, similarly electrical conductivity also low at low temperatures and increases at high temperatures. And how the production of silicon carbide is done actually? We take 60% sand and 40% coke. Coke you must have listened to the previous sessions. There also coke was there, where in the iron extraction from the iron ore coke was used, and also in steels that is there. So carbon is the main constituent there. 60% sand and 40% coke, all types of natural things are here. Then we also mix sawdust and salt. So 60% sand, 40% coal, some sawdust and some salt, and then further it is heated in electric arc furnace at a temperature of about 1425 degrees centigrade. So from this we get silicon carbide. It is removed from the furnace as a mass of interlocking crystals. So it is crystalline type, and the crystals are interlocked with each other. Various shapes of this SiC can be obtained by grinding and by mixing them with certain binding agent, and this binding agent will help them to coalesce together, and further they can be shaped and fixed. And one more production of SiC is there, that is thin wall components or coating type of SiC. How they are produced? This is done by decomposition of gas mixture containing both silicon and carbon on a heated substrate. Fuel elements of high temperature gas cool elements are produced by this method. Also recently it has been seen that SIP casting is also being used for preparation of silicon carbides. So after silicon carbide, there are certain other things like silicon element itself, silicon nitride. So these are very good binding materials. So we discussed in case of silicon carbide production binders. So this silicon nitride itself can act as the binder. So silicon carbide can be used only up to a temperature of 1500 degrees centigrade, because otherwise it loses its bond strength. Silicon nitride bonded SiC. So there is a difference now. If you are using only SiC, then it cannot be used above 1500 degrees centigrade. But as soon as we add silicon nitride, then what will happen? It will retain its strength at much higher temperature and will also show much better shock resistance. So just add silicon nitride and silicon carbide, then you will have a much better performance at high temperature. Silicon carbide refractories are characterized by low thermal expansion and high thermal conductivity. So it has low thermal expansion, that means it has very good strength at high temperatures, it is not going to deform, and high thermal conductivity means that it can also pass the temperature, so that is a good thing. Also these have certain drawbacks, like they tend to oxidize slowly in air at a temperature range of 900 to 1300 degrees centigrade. So in this temperature range, oxidation can take place, so it can result in rusting and corrosion. So this is not a very good thing. After discussing the silicon carbide and nitride, we now move on to boron carbide. There are certain properties like it has great hardness and excellent wear resistance, high strength is also there, and this sintered product is porous and has coarse grain structure, so it has low tensile strength. Obviously, we have discussed in the iron carbon diagram also, and previous things discussion also, we have seen that coarse grain and fine grain were there, so recall that. So with coarse grain we get a low tensile strength. So the drawbacks of boron carbide, the drawback is that it readily reacts with oxygen at a temperature higher than 980 degrees centigrade, and thus its application has to be restricted to this temperature, although its melting point is around 2450 degrees centigrade. And the second drawback is that it is very costly. Certain applications of boron carbides: it is highly useful in nuclear power reactors because of its capacity to absorb thermal neutrons. So if you have read about the nuclear fission reaction, so you will be knowing about this effect. Boron is used there and it absorbs thermal neutrons. In hot pressed condition, it can achieve a tensile strength of 400 megapascal. So in hot pressed condition, it gives a very good tensile strength. Short blast nozzle and ballistic armor. See, these are some of the applications of boron, this carbide. And for temperatures in close vicinity of 2000 degrees centigrade, carbides of zirconium, tungsten, molybdenum, thallium, niobium and selenium are used both in reducing or neutral atmospheres. Carbides of titanium, vanadium and niobium can also be used up to temperature of 2500 degrees centigrade. So these were some of the other elements that can be used as carbides. Then borides. So we discussed about boron carbide, so this is a different thing, this is boride. And the property of this is that it exhibits very high hardness, has good chemical resistance, and melting point ranges from 1800 to 3000 degrees centigrade. But again, their application is limited to temperature of 1400 degrees centigrade, because again the same thing, they begin to oxidize. Borides of titanium, zirconium, chromium, molybdenum and tungsten, they find industrial application, very wide industrial application. Further we discuss about the nitrides. So nitrides also have very high melting point, but again they also begin to oxidize at low temperature. So these oxidize at low temperature actually. The other ones were oxidizing at high temperature, borides and all. And it has got poor resistance to chemicals, so it has got quite a number of drawbacks. Boron nitride has a graphite structure and hence exhibits lubricating properties. So this is one good property, that it is a crystalline type of structure like graphite layer formation, and it can be used for lubricating purpose. A form of boron carbide known as borazone, produced by compressing under high pressure of 68,000 atmospheres. You can just imagine how high is the pressure at a temperature of about 1700 degrees centigrade. This is hardness equivalent to that of diamond. So this is one product, the borazone. It has same hardness as that of diamond. And borazone also has a good resistance to oxidation. This is very nice property. So rusting and corrosion effect will be lessened, and it can withstand a temperature of 1950 degrees centigrade. Boron nitride actually differs from ceramic in that it has soft laminar structure. Ceramic was brittle and its structure was not soft. So one application comes in here for boron nitride. Since it is soft, so it can be machined. Anisotropic boron nitride crystals can be deposited on a substrate to obtain coefficient of thermal expansion which may be 100 times greater parallel to substrate than perpendicular to it. So it depends on the direction. That's why anisotropic. In different directions, different kinds of properties we are getting. So in one direction thermal coefficient is 100 times greater than the other direction. And such deposited crystals also cause the composite to behave as thermal conductor better than normal ceramic. And one more thing we can note in case of this boron nitride is that many molten metals do not wet boron nitride. So if a certain molten metal is there, then it will not have any effect on boron nitride. So for this reason, it can be used for making crucible for melting metals. Yes, it can be used as a vessel because melting metals will not affect it, so it can be used for storing them. The cubic form of boron nitride is very hard. This is another property, and since it is very hard, it can be used as an abrasive. Then we discuss about the silicon nitride, another nitride like boron nitride and its production. So alternative fabrication methods are there, but they are costly. So silicon powder is compacted in nitrogen atmosphere and is sintered to give porous reaction bonded silicon nitride. So this is one process. A costlier method is hot pressing of silicon nitride powder mixed with 1 to 15% magnesium oxide, which provides liquid phase at sintering temperatures. But here fine structure is obtained and thus the product is strong. So silicon nitride has certain advantages and disadvantages, and its derivatives are also there, so they also have advantages like high strength and hardness, good refractiveness, low coefficient of thermal expansion, high thermal shock resistance, and high resistance to oxidation due to formation of silica film. SiO2 we have read earlier. And what are the drawbacks? Its fabrication is difficult and thus its use is not that common. And it is not easily sintered, that means it cannot be coalesced into one, its particles cannot be coalesced easily, and it begins to dissociate above 18-15 degrees centigrade. So now after discussing all these things, we discuss certain other things like silicates and sulfides. So silicates, what are the properties? These are particularly notable because of their resistance to oxidation. So silicate have very good resistance to oxidation, and their resistance is obtained by because of the formation of a glassy silica coating on the surface, but they have low melting point. And what about the sulfides? Sulfides of cerium and thorium are used as crucibles for molten metals, like we have seen in case of boron nitride also. And these are prone to oxidation, thus they must be used in vacuum or neutral atmosphere, because otherwise oxidation will affect them and corrosion and all those effects will come in. So one more thing that we are going to discuss in today's session is the carbon and the graphite. So carbon and graphite are also very excellent refractory materials, and the drawback is that they can readily oxidize. Hence they are used only either in the reducing or neutral conditions. So if we are using carbon and graphite, then only neutral condition can be there or reducing condition can be there. Oxidizing atmosphere cannot be there. So graphite is a more stable form of carbon actually. Amorphous carbon other than graphite is converted into crystalline graphite on prolonged heating at about 25 degrees centigrade. So we can change an amorphous carbon to graphite type. Graphite does not melt but sublimes at a temperature of 4200 degrees centigrade. And carbon and graphites are highly resistant to acids, alkalis and all solvents except the oxidizing ones. So reducing atmosphere is very much needed and no oxidizing atmosphere. And what are the applications of these? Graphite we know is a very common thing, and it is employed at high temperature as rocket nozzle or nozzle throat insert. And the graphite nozzles, they are coated with silicon carbide, which we have read earlier, and molybdenum silicate, or impregnated with zirconium. Why? To improve the oxidation resistance. And molten zirconium with which graphite surface is impregnated forms zirconium carbide, which has good chemical bond with graphite surface. The outer surface is oxidized to zirconia, thus it prevents further oxidation. So it protects our graphite. Carbon and graphite are also used in industry in both fabricated and non-fabricated forms. So in fabricated forms, they are employed as materials of construction, like electrodes and refractories, and also chemically resistant equipment and nuclear reactors. So how a certain drawback is removed for this carbon and graphite we are discussing now. Carbon and graphite shapes produced by common techniques are very porous, so they can be made impervious to fluids. How? By impregnating with synthetic resin, usually of phenolic type. Phenolic meaning it is alcohol based. If you know certain amount of chemistry, you can know that OH bond will be there, and then this resin is cured at high temperature. So in that way we are removing the drawback of porosity. And non-fabricated carbon, how it is used, we can see here: lamp black, carbon black, activated carbon, graphite diamond. All these things are non-fabricated. Lamp black and carbon black are used as fillers and pigments. Activated carbon is used as a crystal in chemical processes. Graphite, we know most common use is lubricant. In batteries also it is used, and for crucible manufacture also. And industrial diamond is used for cutting tool because it is very hard. And boat and carbonodo are common industrial diamonds. The tensile strength of carbon materials actually varies with type grade and method of manufacturer, and the tensile strength is between 80 to 250 megapascal at room temperature. The strength approximately doubles at a temperature of about 2450 degrees centigrade. And carbon as graphite also possesses low thermal expansion and high thermal conductivity. Both these properties will enhance resistance to thermal shock. So graphite can be easily machined because of its type of structure, whereas other forms of carbon are not easily machinable. And this is commonly employed as an electrical conductor also, because it has got good electrical conductivity and it has got low specific resistance. And largest tonnage of carbon and graphite is used in metallurgical and electrochemical industries. And how? They are used as anode in arc melting furnaces. So in this session we discussed about the refractory materials ranging from the ceramics to different types of carbides, different types of oxides, nitrides, sulfides and silicates. We also discussed various properties of these things and their applications. How these properties give us different kind of applications. All these things we discussed in this session. And this unit will comprise of I think one or two more modules besides these two which have been covered, and you can see those things we will discuss in the next sessions. Thank you very much.